Hello everyone, and welcome to our first Brooks Bell webinar. And first of all, let me thank all the IT guys here in Brooks Bell who helped us set up this event in a speedy time. And today I'm going to talk about marine coatings. So essentially, we will highlight our in-house expertise and skills in dealing with issue related to marine coatings. And the title of the presentation, as you can see, is Marine Coating, the first line of defense for corrosion and cargo protection. But first of all, let me introduce myself. I'm Luigi Petrone. I'm a senior scientist and also a senior coating consultant at Brooks Bell, and I'm based in Singapore office. And I am essentially a chemist by training. I got a bachelor degree and PhD in chemistry, and then I also got a diploma in coatings for corrosion control quite recently. In terms of experience related to coatings, marine coatings, I have about 15 years at the time, of 15 plus years experience in synthesis, analysis, and working on different types of coating failures in the marine protective coating industry. Previously, before joining Brooks Bell, I carried out academic research in various universities around the world. I've been in Sweden, Singapore here, Harvard, and also Santa Barbara, where I developed so-called SLIPS coating, which were anti-foul and antibacterial coating technologies. And other jobs, I work in collaboration with major paint manufacturer, like International Paint, on the development of these novel anti-fouling coatings. I'm a member of various affiliations, like a chartered scientist, a chartered marine scientist as well. And I'm a certified inspector for marine offshore coatings, as well as yachts and super yacht coatings. So why talking about paint? Paints are expensive, especially marine paints applied to ships, and they make up about 10 to 15%, depends on the type of ship, of the total cost of a new building. This will include the actual paint, the liquid paint before application, as well as the application process, surface preparation, and so on. So it's important to get the job right, because failure can be really expensive. And the baseline cost of paint was calculated to be, this is back in 2013, about $10 per square meter. But it's even more expensive when it comes to maintenance and repair. This can go up to $25 per centimeter square. Please note that. So paints, there are many different types of paints. Sometimes people believe that there is only one or two types of paint for ships, but each ship structure is coated with a different paint, or with a different layers of paints, as I will show you later. For instance, here we can see cargo holds on a bulk carrier. Cargo holds will have a special paint which can resist abrasion, impact, and to some extent also corrosion. But on tankers, you will need to have totally different paint. In cargo tanks, cargo oil tanks, you will have paint which will resist chemical attack as well as corrosion. Superstructure here on a ship, they will have to resist corrosion, of course, as well as the ultraviolet and the heat. Ballast tanks, of course, in a humid or wet environment, they need to resist corrosion, and on decks, depending on the type of ship, they need to resist chemical attacks, but certainly corrosion, UV light, and heat. So these have to be very high-performance coatings to perform in aggressive environments. But let me spend just a slide to describe the outer hull. The outer hull of the ship is divided in different sections depending on the environment. The environment can change on the outer hull. On the top side up here, the top side, the paint should resist salt spray, so UV light, of course rain, and sometimes impact. So the type of coating system to be applied here on the top side, it will have to be an anti-corrosive, followed by an abrasion-resistant coating. The boot top is a bit more complicated because boot top has intermittent immersion times in seawater. Depends if the ship is in ballast condition or not. It has to be UV resistant and also resistant to impact, abrasion, and mechanical damage. So here you can have ship owners can choose different system just to apply an anti-corrosive. They can also apply an anti-fouling on top of it, or they can apply an abrasion-resistant paint, depending on how much money they're willing to spend. And then we have the vertical sides and the flat bottom, which to some extent will have the same type of paint, but there are slight differences because the so-called fouling pressure will be different on the vertical side compared to the flat bottom. So, but certainly there is an anti-corrosive paint at the bottom, and on the top there will be an anti-fouling paint. Generally, when we talk about anti-corrosive paint, these are always epoxy-based paint. And when we talk about abrasion-resistant paint, typically is a polyurethane, but can also be an epoxy paint, like in cargo holds. So what's in a can of paint? Paints are very complex mixture, but they certainly require a binder, so-called, and the binder gives the name to the paint. So you will have epoxy paint because you have an epoxy binder, or an alkyd paint, or a chlorinated rubber paint, or vinyl paint. There will always be pigments and extenders as well. They provide the color to the paint, of course, but they provide other properties like anti-corrosive properties, or for instance, on super yacht, the gloss, for instance, gloss control, or abrasion resistance. There are almost always solvents, although we're moving towards solvent-free paint because of environmental regulation. The solvents only aid the application. So they only aid the application of the paint, and then they will evaporate. Nowadays, there are more and more water-based solvents, water-based paint, but typically you find xylene, alcohols, acetone, or methyl acetone. There is also another category of compounds called additives. These additives make up about 1 or 2% of each paint mixture. And they have an important role, like they are defoamer, so they prevent the formation of foaming, can be anti-fouling, as I will speak about later, or flow and leveling, so make sure that the paint will flow and wet the surface, so the paint can adhere well and homogeneously. So, as I said, we talk about usually in marine paint about coating system, not just about a layer of paint, but there will be multi-layer. So it's a multi-coat system. You will have first the metal, which is treated and clean. But I'm not going to talk about this in this seminar. There may or there may not be a so-called shop primer, which is a very, very thin layer, which is applied soon after the metal is prepared in yards. This helps with the corrosion protection of the underlying metal. Then there will be a first layer, first coat, which is typically helps with anti-corrosive properties or with a high build, so helps with the thickness of the paint system. Then there will be many other paint layers. At the top of it, usually there is a so-called top coat, or they can also, so it's also called finish coat. And this is really the layer that gives the performance and the property to the coating system. So if you have an anti-fouling paint, here is where your anti-fouling coating is, typically. And as you can see, the multi-layer system, it basically creates a barrier. And this is the physical barrier that protects the underlying metal from corrosion, from the permeation and diffusion of oxygen, water, and other corrosive species towards the underlying metals. Here is just a typical example of a cross-section of this anti-fouling paint. So you will see that there is a metal here. On top of it, there is a first layer, typically epoxy, 2 or 3 layers, various thicknesses. Then there may or there may not be a tie coat. And after this, there are various layers of anti-fouling paints in red. So this just to give you an idea of the complexity of these coating systems. It's not just a monolayer or 2 layers. Sometimes it's 2 layers in cargo holds, but they can be very complex. So we have to analyze paint during our forensic investigation, and we use an array of laboratory analysis. We go from more, simple in a way microscopic observation. Just we look under a microscope to see how many layers there are. And then we can use more expensive microscope called electron microscopes to find out also, to look at the porosity of the paints, for instance, or to look at the element in a paint, like with these X-ray techniques. So we look at which elements or atoms comprise each layers. Other techniques, other X-ray based techniques will give us an idea of which crystals are inside each layer of the paint, and these are related mostly to the pigments, also the extenders. And infrared spectroscopy is quite useful to find out the fingerprint of the paint, so which type of binder it is. So is it an epoxy paint, is it a urethane paint, or is it an ester paint? So these are sort of, in my view, these are like the basic laboratory techniques to carry out an analysis of paints when we do our forensic investigation. I would like now to highlight the difference between code inspector and coding expert. When I deal in jobs as a code inspector, when I'm called as a code inspector, for instance, in hull fouling cases, you can see here a picture of hull fouled with these are barnacles. What I usually do, I just report on the extent of fouling or the extent of coating breakdown due to fouling. So essentially, this is the job of a code inspector. But when I deal with this job as a coating expert, it's a totally different job, because then I'll be asked what caused fouling, and if the coating system is damaged, is this damaged or not? And if it's damaged, how to repair it? I will touch more on this later on in this presentation. Another example here of the difference between an inspector and expert, mostly in, for instance, ballast tanks or cargo oil tanks, there are so-called PSPC regulations that some of you might have heard of it. And as a code inspector, I need to report on the basis of this PSPC regulation if the code is in a good, fair, or poor condition, for instance. So the coating must be kept always in a good condition as for the criteria of these regulations. Or I might be asked on the extent of blistering, on the extent of cracking or coating breakdown. But as a coating expert, I'm usually asked about the causation of the blistering, or causation of cracking. So it's much more complicated and complex as well. And once we have a damage, how to conduct repairs, because this will affect, of course, costs and for the clients and for the ship owners. Is it like a simple patch-up repair, or we need to have more extensive repairs? Let me give you just some example of what we deal with in Brooksville. So, for instance, in cargo tanks, paints typically applied in cargo tanks are epoxy based. You also find the zinc silicates. These are inorganic paints or just stainless steel, which is uncoated, which is very expensive. But the great majority of chemical product tanks are coated with epoxy based, so some sort of epoxy paint. Epoxy paint is used to protect the underlying steel, as I showed before, against corrosion, but also to avoid cargo contamination when changing grades, especially. So when one cargo is offloaded, you want to make sure that there is no cargo left on the surface of the tanks, which may contaminate the subsequent cargoes. And the epoxy paints are really, really smooth and should not allow absorption of the cargo. So they facilitate also cleaning of the tanks. Just to give an idea of what they look like, I mean, you don't have to know chemistry here. Just follow here the circles. This one will be the epoxy ring that is used. Epoxy paint is usually so-called two-component paints, and they are mixed and then they're sprayed and applied on the surfaces. So the epoxy ring here will react with the so-called curing agent. In this case, is an amine, and they cross-link and chemically form new bonds. So this is just one molecule of one curing agent reacting with 4. So this will be cross-linking. But if you try to imagine in 2D, this is what happens, and you have lots of cross-linking. And this will be an epoxy paint in 2D. Just to give an idea of what it might look like, it looks like in 3D. Starting from the bottom here left, you have like, imagine this would be maybe pure epoxy paint. As you go more and more and more on, if you increase the cross-linking of the paint, the cross-linking density of the paint, You will increase also the resistance of the paint towards different cargoes, the chemical and corrosion resistance. So you will go to more polyisocyanate epoxy, so-called, and more Novolac, or epoxy-phenolic Novolac. But as you move on this line, higher density of cross-linking, this will be higher resistance, but it's also higher cost. So it really depends on the owners of the ship which coating they want to apply. But typically they will go for Novolac nowadays. Recently, there are mostly, in my experience, 3 paints for cargo tanks, which in a way dominated market. These are the Marine Line 784 from APC, Advanced Polymer Coatings in the US. Then there will be Interline from International Paints, and then Jotun developed Tengard Flex Line. These are the latest coatings. These are based on slightly different chemistry, but always epoxy based, as I showed before. The advantages of these 3 new paints, in my view, are low cargo absorption, so the cargo will not really absorb on every paint. By my experience, every cargo is able to absorb on every type of paint, even though they claim otherwise, manufacturers. These paints do have superior chemical resistance, it is true, and they are easier to clean. So they also have shorter recovery time when changing grades. But they also have big disadvantages. The disadvantage is that these paints are highly cross-linked, which means that they have poor flexibility compared to the previous generation paints. So this makes them a bit more brittle, you can imagine. And they're much more sensitive to the preparation of the metals, because surface preparation, and to the environmental condition like relative humidity or temperature at the yard during paint application. So the error, margin of error is very small. It's very small for the application of these paints. If they are applied outside of this small margin, things can go very wrong. And one important thing that these paints are applied are cured after application by hot curing, so-called. This is carried out previously just by immersion in hot water, but we found out that hot water curing is not very effective and can damage the paint. And nowadays, especially Marine Line, they're moving towards hot curing with the hot air. So let's see what can go wrong with these paints. As I said, the cargo, once the cargo is loaded in the cargo tanks, some of the cargo will be absorbed in every paint, so will permeate through the paint into the coating. And after the cargo is offloaded, the cargo should leave the coating, but it's not always true. It really depends on how much time is allowed for this evaporation of the cargo, the venting condition. And if it's not done correctly, this can cause cross-contamination issues and therefore claims with the next cargo. Another issue is the cargo flexibility in itself, the flexibility of the paint, of the coating. Once the molecule of the cargo penetrates through the network, through the 3D network of the paint has to be flexible enough to allow the cargo to enter, also to exit, to be released. But sometimes you can have the formation of cracks or microcracking, so damage caused by microcracking, as you can see here, as the cargo penetrates through. So this is what microcracking looks like. You can see you are at the millimeter, it's not really micros, you are at the millimeter scale here. So here you have a crack here, you have another crack here, so they're very difficult to see. So you need to be able to illuminate the coating in an adequate way. Sometimes you use zoom, camera with a zoom. So you will be able to see all the cracks here. These are micro cracks. Sometimes difficult to spot, and sometimes, you know, owners or other, they say it's not a big deal. But actually after a while they develop, they grow. And you can see here the red stain. This is actually rust. This actually means that water and corrosive species have penetrated through the crack to the micro crack, and they reached actually the metal substrate. So this is just bleeding from the metal, rust bleeding out. So this means that the damage is already deep and reached the metal substrate. And after some time, the cracks can expand and coalesce and cause total failure of the cargo hold or the paint in the cargo tanks. For this case I investigated recently, the damage was up to about, the claim from the shipyard to repair was about $2 million US. Another common type of damage is blistering. This is always found in coating which are found in immersion services or high humidity areas, like in ballast tanks or in the cargo tanks, for instance. And the blister is just filled with a liquid, often water, but can also be a gas. So sometimes it's possible with a macro syringe to extract the content of the blister, so we can analyze it and we can have a better idea of what caused the blistering. So these are localized paint detachment. You can see it from the picture where in this case, a liquid like water lifts the paint and detach from the substrate. And after a while, they tend to pop. And in this case, you can see, like for the example we saw before for cracking, macro cracking, you have bleedy and the rust deep down to the metal substrate. And this one can grow over time and cause a large breakdown of the coating. I just want to show you a case study of a recent case I've been involved. This case of blistering cargo tanks. Just to cut the story short, the liquid inside was found to be water. Here just image with water finding paste. So there was water inside the blisters. So usually during the investigation, I will focus on what is the source of the water, first of all. There are many cases, many causes for blistering. That's why it's not really straightforward usually to find out the causation of blistering. So require experience, require knowledge with sampling, require knowledge with the data analysis, interpretation. And in this case, I've investigated all different types of causation. And trust me here, but none of the general causes was related to the blistering. So the paint was applied at the new building in the correct way, surface preparation was correct, and there was no issue with the quality of the paint. And looking at the history of the cargoes carried on the ship, I noticed that ethanol has been carried before the appearance of the blisters. So these are clue already. So ethanol is an aggressive cargo and can permeate paints. I will explain in a minute why. But I found that ethanol was carried only in 4 of the cargo tanks, and the blisters were found only on these tanks. So easy conclusion is that the ethanol cargo was related to the presence of blisters. Because ethanol, as I said, an aggressive cargo, ethanol can mix with water, is miscible with water, can contain water, and water will cause the blistering and the corrosion of the substrate. So the question was at that time if ethanol was the cause of the blister in itself and the ethanol caused the damage of the paint. Why is ethanol an aggressive cargo? Here I listed a few of the aggressive cargo, the common aggressive cargoes carried on chemicals product tankers. One thing they have in common is the size. They're all small chemical molecules. So either they have one atom, one carbon atom, 2, like in the case of ethanol, or 3 carbon atoms. And they're usually small because they need to be able to penetrate those pores into the 3D network of the paint. And also they have a chemical affinity for the epoxy paint with their oxygen, and they are able to penetrate the paint and not to be repelled from the paint. And they're water miscible as well, so they carry water with them. Each paint is important to remember that each paint comes from the manufacturer with a so-called cargo resistance list, where it tells you which cargo can be carried with this specific case paint and in which condition, and all the restrictions that apply to each cargoes. And in this case, for ethanol, I won't tell, of course, which paint but for ethanol, could be carried with a maximum of 1% water. And then I transformed into a cargo scientist, which is my other expertise. So I We took samples and the representative sample from all the tanks, and we analyzed the sample with the correct standard, and we found out that the water content in each tank, on each sample, was well below the 1% by weight that was in the cargo resistance list, all samples, all tested samples. So ethanol itself was not the cause of the blistering of the cargo damage, because the water content was below the maximum specified by the manufacturer. So where did this water come from then? Then I reviewed the tank cleaning procedure. So after the ethanol cargo is offloaded, water typically can't be used to wash the tanks. Otherwise, they will cause a blister right away. In this case, correctly, they inerted the so-called, they say inerted the tanks. So I assume they use an inert gas to vent the tanks until all the ethanol left the paint in the cargo tanks. So also the cleaning procedure was correct. And then next step will be to review the inert gas. So then I found out that the ship was equipped with an inert gas generator, or IGS. And what struck me was that this IGS, this inert gas, was not really inert, but actually contained water droplets up to 1000 ppm, which is pretty large. So this is what happened in this case study. The tanks, cargo tanks, carried an aggressive cargo that penetrated the coating. So you have swelling of the coating, which is okay, which is normal. So ethanol can always do this with any paint. And then ethanol is a water soluble. So then the tanks were inerted with this gas, were vented with the gas, carry water droplets, and the droplets permeated through the ethanol, because the ethanol had expanded the paint, ultimately reaching the metal substrate and causing the blisters. So this was the cause of the blister, and the wrong definition of inert. So the crew thought it was inert, but actually the gas contained a water droplet. Another type of work we do here, I do here in Bruxelles, mostly assisting our master mariner in collision cases, is to take paint or paint samples and find out if this paint can be related to one ship or to another ship in collision cases. Here, for instance, a recent case I've done with my colleague here, Captain Ivan Todorov from Singapore. There were markings on the bow of a tanker. So we had to figure out if this came from a fishing vessel which was found, which sank over here in Singapore. And what we did, we took samples in various locations where the marks were present and of intact paint. And then these were analyzed first simply by optical microscopy. So just zoom in and see what's in there. And we found the remains of white paint here on top of the anti-fouling paint of the tanker. So here you have the paint of the tanker, and here you have the white paint. So definitely there was a paint from another vessel, so there has been a collision. This was difficult to see without the microscope. So the lab analysis confirmed that there was another paint, but which kind of paint? Chemical analysis of this paint, I won't go now into the detail, there is no time, but the chemical analysis actually revealed that this was a paint not from a commercial vessel like a tanker or a bulk carrier, but I was able to identify that it was a paint from a fishing vessel, from the biocide present in it, from the extender, the filler, so from knowledge of the chemistry of the paint. And this was likely the paint from the vessel that sank, really. So there are always major differences between paint applied on different vessel types, and also for the same vessel, different companies will have different paint compositions. So knowledge and the deep knowledge of this chemistry allows us to make comparison and to help and assist our master mariners in these collision cases. Another type of paint we work quite extensively here in Bruxelles is anti-fouling coatings. Just very briefly to give a background on anti-fouling coatings. The goal of antifouling coat, the antifouling paint, goal number one is to minimize the surface roughness. Why surface roughness is important? Because the friction resistance of a vessel is largely controlled by the roughness of the outer hull. If you minimize the surface roughness, you will minimize the frictional resistance, and actually you will also minimize the fuel consumption ultimately. So as the resistance in water increases, also operational costs increase. So there are two factors that control control surface roughness. One is the physical, so actually the physical profile, the roughness of the paint in this case, of the outer hull. And the second, you have a biological cause, which is fouling, which I will describe in a moment. The combination of the two will give you the total roughness of the outer hull. And this larger roughness will result in a increasing drag, increasing fuel consumption, of course, but also an increase in the gas emission of the greenhouse gases and operational cost, of course. And one of the topic, which is quite a hot topic now with ballast water convention and other new regulation, is the translocation of invasive species. There are largely two types of fouling. One's called soft fouling, which is mostly slime of algae. As you can see here, this green line, it tends to grow mostly on the vertical side because it's the one more closer to the sun. It's like plants, they're like plants and they need the sunlight to grow. And they account for 1 or 2% increase typically in drag when they grow to this condition. And the next fouling is called hard fouling, which is the one with a hard calcareous shell, like barnacles mostly. But you can also find mussels or tube worms. And they account for up to 40% increase in drag and also fuel consumption. And you can see this is one of the pictures I took of a colony of barnacles which grew on a hull of one of the vessels I inspected. So they can grow, they become pretty large. So that's why the drag and the resistance in water can increase so much. So we don't want this to happen. And that's why we use antifouling paints. Now, very, very briefly, there are different types of antifouling paints, but most common ones perhaps are so-called biocidal antifouling paints. So they work by releasing biocides. Essentially, it's a poison, they kill marine organisms. That's how it works, according to regulation, of course. They are heavily regulated. And they're mostly divided maybe in 3 categories, I show you here. But by far, the most used one is copper in different forms. So copper is contained in most biocidal antifouling paints. There are also different types of biocidal antifouling paints. We can just classify them in three large groups of so-called CDP, controlled depletion polymer. Then you go self-polishing comolymer, and then hybrids of the two. And the SPC are really the most expensive one on the market. So the price is quite high, but the performance is much better. It's far superior than the CDP. But really depends on, first of all, on how much ship owners are willing to pay, but it also depends on the trading partner of the ship. If the ship trades in an area where there is not much fouling pressure, then there is no point to buy an expensive SPC. So low end of the market CDP will do in that case. Right, hull fouling disputes. We get involved quite a lot with the hull fouling disputes, and we have different expertise, and we combine different expertise and skill set here in Bruxelles to deal with these hull fouling disputes. We have some of our mastermind can deal with vessel underperformance caused by hull fouling, for instance. We have in-house marine biologists who can deal with the growth rates, for instance, of barnacles, which is pretty important to understand at which time barnacles may have attached on a hull. And then from a chemistry point of view, from the coating knowledge, we deal with the aspect related to the antifouling paints and to antifouling coating system as a whole. So typical question we get, as you can see here on this picture, this is the flat bottom of a vessel at dry dock. You can see here that you have marks here. These were caused by underwater cleaning. Underwater cleaning is typically conducted when the vessel is at anchorage in some location around the world. So divers go underwater and clean with rotating brushes, typically the hull from fouling. So here, the first question I ask sometimes is this damaged or not? This is one of the contentious questions sometimes. Can be straightforward, but not sometimes it's quite difficult to ascertain. But typical question is if it's cleaning damaged the paint on one side. And then other parties might come up and say, well, wait a second, maybe the paint was not correctly applied. Maybe the paint was already weak in some spot and came off during cleaning. So it can be quite contentious to understand if cleaning caused the paint damage or if it was the paint itself was not applied correctly. And this can be quite expensive because imagine that once the paint is this condition, you have to dry dock the vessel. It has to go to dry dock and you have to basically full blast the entire hull and reapply a new coating system. So it can go up to $1 or $2 million US on, again, the entire operation, depending on the type of paint that the owners decide to apply. Other question, like in this case, you can see that the dark red is the top coat and the light red is the coat just underneath. So most likely either another anti-fouling paint or an anti-corrosive paint or a tie coat could be. So the question we are asked here typically in this hull fouling dispute is whether once again cleaning detached this layer, this top coat. So you got this intercoat delamination, or maybe the top coat was not applied correctly. So and detached that came off at the time of the application. Maybe the environmental conditions were not right, or this layer was dirty and the top coat did not stick as strong as should have been. Or perhaps the two paints were incompatible. Maybe they are from different paint makers. So they were incompatible, they needed a tie coat in between. Or once again, there is one more possibility that maybe heavy fouling. So fouling can be very heavy, can be several kilos in some location. So heavy fouling in this location caused the detachment of the paint. So this case can be quite complex. And finally, the question that we get the most is whether the fouling was due to a long stationary or so-called idle period as well. This is typically specified in charter parties, the length of the maximum length of idle period, after which the paint stops working. So anti-fouling paint, especially this biocidal anti-fouling paint, work typically when the vessel sails at a certain speed, at a certain minimum speed. Once the vessel is stationary or idle, the performance, anti-fouling performance decreases over time until it stops. Typically after 2 weeks, can be 3 weeks, can be more, depends on the quality of the paint. So this is one of the questions we get asked quite a lot to investigate whether the fouling was caused to the stationary period, or once again, whether the anti-fouling paint did not perform for a number of reasons. So the take-home messages from this presentation, the claims, first of all, can be quite expensive because sometimes they require dry dock of the paint or full blasting of the entire area, or very expensive quality of paint. And investigating the cause of paint failure is never easy. It's always challenging because it can be caused by multiple factors or some 2-3 factors together sometimes. So it's difficult to understand which one is the most likely causation sometimes. And as you can see, it requires so-called holistic expertise or multi-skill set to investigate these issues. So definitely we need knowledge in marine paints, obviously a deep knowledge, also on the various mechanisms of paint failures. Then we need a deep knowledge on the laboratory techniques because we need to instruct various labs or our own lab in the future on which analysis to do. So there has to be adequate and ad hoc analysis. And we need to be also expert in the interpretation of the analysis and what it really means and how they relate to the observed failure. And we collaborate very much, and I'm always thankful to our master mariners, our naval architects, and also our marine engineers, because we work very closely with them when the failure relates to ship structure, for instance, or ship's operation, as you saw the cleaning in the case study I showed before. And we also have in-house marine biologists, as I mentioned. And with this, I thank you all very much for our first webinar.